first speaker this afternoon is Fabio Tal from the University of São Paulo, and he's talking about the topological horseshoe for surface moves. Please.
Thank you very much. I would first start by thanking this year. I'll start the organizers for the invitation. It's a pleasure to be here, and it's a pleasure to be in a conference in honor of Wellington. Unlike most of the people, I didn't have much contact directly with Wellington. I mean, we crossed paths, but we never had that much direct contact in IMPA or in studies. But it's undoubtable that he formed and shaped with a large part of the dynamical systems community, and we can always feel the fact that he had in the community here in Brazil. So I'm very thankful to be talking here, and start today by talking a little bit about topological horseshoes for surface homeomorphisms. It's a joint work with Patrice Lecalves.
A bit louder.
A bit louder? Okay, no problem. I'll talk, try to speak very loud. And this is a little bit uncomfortable to speak. And the title of the talk is Topological Horseshoes for Surface Homeomorphisms, but it should be the honest one should be no topological horseshoes for surface homeomorphisms. This is the main subject I'm going to talk about.
Oh no.
I actually enjoy being interrupted. Kinds of keep me in my rhythm.
Yeah, don't worry. We will not let you fly.
Okay. So, the first thing I should define what is a topological horseshoe. My first wish was to say that I should define it like a dog. I mean, people know a dog is a dog, but it's difficult to define. But let me give a precise statement. And I'll just say that I'm only going to work with dynamics on surfaces, and it's always going to be orientable dynamics on surfaces. So this is a standing hypothesis. I'm not going to write down orientable any map that I have. So I'll say that I have an F from S to S, a topological horseshoe. Lambda, if there's a power, k, such that Fk restricted to lambda is semi-conjugate to the shift onto symbols. This is the first thing, so that the dynamics here is semi-conjugate to the shift into symbols, and also that each periodic point omega, which belongs to sigma 2, has a periodic range. Meaning that if I have a periodic point for the shift, then I'm going to find a periodic point for Fk with the same period. So in some sense I have this implies that I have positive entropy. It also implies that I have exponential growth of periodic points. Yes?
Yeah, I don't understand the restriction on orientation
No, I don't need the restriction.
Because it's the same, yeah. You take the square and if you have there,
no, I didn't need the restriction for rotation preserving here, and I didn't need to restrict this to be on the plane anyway.
Yeah.
But for the rest of the talk, it's usually going to be on the plane. So this is a definition that should work on metric space. And so I'm just saying that a map that has a topological horseshoe is a map that, for instance, has positive entropy and has a lot of periodic points, the exponential growth of periodic points. And for surface dynamics, there's a very strong relationship by a theorem from Katok that says that if the entropy of F is greater than 0, and F is C1 plus epsilon d field, then F has topological horseshoe. So sufficiently smooth. If you have positive entropy, you have topological horseshoes. But in general, this is not the case. This does not hold for C1 dynamics. Look, like you actually have a horseshoe
sorry.
here.
You say it does not work for C1. You know that it doesn't work.
Yes, there is examples that C1 features that don't have topological, that have positive entropy. You have Mary Ree's example, and then Béguin, Corbusier.
Yeah, but that's C0.
Yes, but then Béguin, Corbusier, Leroux have several examples which are C1. So they have all this machinery of how to build C1 examples where this does not hold.
What is going to be not?
Yes. With no periodic points.
Yeah.
So, and
Sylvain, you mean another?
Huh?
Sylvain, another.
C1 again. Béguin. Béguin, Corbusier. Actually, here is a horseshoe, meaning that this is not a semi-conjugacy, but it's actually a conjugacy relation. Okay, and the question we were interested in answering was, okay, so this is a very good model. Having a horseshoe is a very good model. So what can we say for the other way around? So what does it mean to not have a horseshoe, or in sufficiently smooth case, what does it mean to not have topological entropy? So can we describe what is the dynamics without topological entropy in the plane? And this is very much related to the talk that Guarino gave before and people spoke before, where you try to describe how they go from zero entropy to positive entropy in 1D. So now we're trying to discuss a little bit of how can you build this passage in 2D, what can you say? But again, this is much less well developed than the 1D theory. The 1D theory is this beautiful, whole, complete theory nowadays. And for this 2D theory, we're kind of going in the way of, okay, let's first start to know just topological results. What's the topological structure? What the topological results you can get there? There's absolutely nothing done in, so we need more metrics. And so the idea here is exactly to discuss, this is why the title of the talk is No Topological Horseshoe, is what can you see that has no topological horseshoes. And first thing we should start with examples so that we have some things in mind. So one examples, you have flows. And we should start, and this talk we're going to be, I'm going to talk about ohmios of the sphere. So instead of doing any surface, since we're starting with the discussion, let's start the discussion with the simplest possible surface, which is the sphere, or the plane is the same. And we are going to discuss about a little bit about ohmios, no entropy on surfaces. And we start with, well, every flow in a surface, in the sphere, doesn't have entropy. And then you have two things which are interesting for flows, is that if it's conservative, it is integrable. Think of the phase space of the pendulum. When you have a well-defined first integral, and then you have, in the general case, it's much more difficult to give a complete description of the structure, but you can give a description of omega limit sets. You have the Poincaré-Bendixson theorem, which is a description of omega limits for flows. And you know where orbits accumulate, and you know a little bit of invariant sets. And what about not flows? And well, even here you can already see some stuff that you can see as omega limits. You can have things which are, for instance, a cycle of fixed points and some orbits which are homoclinic to these fixed points, and then your flow sort of accumulates around here, so that the omega limit set is this cycle of fixed points and orbits of which are limited to the fixed points. You can find something which, for instance,
Change
yes,
the two.
The two.
you can have a cycle and you have a irrational rotation in this cycle, so you're rotating irrationally here. So irrational. And well, this is the omega limit of itself, so you have a trajectory which is rotating with some irrational average speed, or just some periodic orbit if you take the time one of the flow. Okay, if you start leaving flows and going to the dynamics now, and for discrete dynamics, not flows, there are a few things which can happen. For instance, you can still, instead of having this just circle of just periodic orbit which rotates with irrational speed, you could have, for instance, something like some periodic orbit P, f of P, f2 of P. This is a periodic point, f3 of P. And around this point, it's not difficult to find examples where you have, for instance, a 10% where dynamics here, it permutes these three sets, and then when you take the third iterate of this, you take a return map, and the dynamic here is kind of irrational rotation. It behaves like irrational rotation. Or you can have something which is like a hedgehog, and the dynamic here around this hedgehog is rotating irrationally around this. So all of these are, in some sense, rotating irrationally around some periodic point. Or you can have, for instance, the whole sphere, and you have two periodic points, and every orbit here rotates around the sphere with irrational velocity, and the dynamic is transitive on the whole sphere. This is called a pseudo-rotation, and you can have transitive pseudo-rotations. But all of these have some irrationally rotating behavior. Pseudo-rotation. This is not a rotation, but it behaves like a rotation because every point has the same velocity.
They have all the same rotation numbers.
All have the same rotation number, and the number is irrational.
So in what sense is it not a rotation? It's a rotation on the.
It's rotation
on the sphere.
in the sphere. If you take out these 2 points, you have an annulus, and everything is rotating in this annulus with the same speed.
Yeah, but so it's a rotation of that object.
Yeah, but the dynamic is transitive, so the dynamic is transitive. So that you have points here that whose orbit fills up the whole sphere. So it's not a rotation, it's not a real motion. And there is another example of thing that can happen, is that you can find, for instance, a map of the, I'll draw this on the plane. You can find some disk here, some disk D1, and this is f of D1, this is f2 of D1, and then this disk is a periodic disk, meaning that it's a disk that returns to itself after some time. And then inside this disk, you can also find another disk, D2, and a dynamic that goes F3 of D2, and then you come back. And then when you go another level inside, then you find another disk here, which is disk D3, and the dynamics by F6 here goes like this, and then comes back, and you find another level inside, and another level inside, and another level inside. So you start with the dynamic of the disk, which is the plane, in a sense, and you find a periodic disk, and then you find another periodic disk inside, and then find another periodic disk inside, and so forth.
But just in one disk, it doesn't correspond to the other disk?
Oh, the dynamics in the other disks need to be the same,
Yeah,
because
so
this is an O-mill sending one.
Typically an infinity renormalizable situation.
Yes, this is, I'll define it, this thing is exactly now.
Typically if the size, if the limit things are points, it will be another odometer.
Yes,
And
and
otherwise it's a
at least
degenerate
it's going to be semi-conjugated to the other matter, but if the limit things are points, the fiber are points, then it is the other matter. So let me just give this definition. I'm going to say that is lambda, which is compact invariant. Ref is topologically infinitely renormalizable. Ref if there exists di, d1 which contains d2 which contains d3, a sequence of topological disks, ni, n1 which is less than n2 which is less than n3, a sequence of integers such that f ni of di equals di and fj of di is okay, not different, disjoint. Is the empty set for 1 less or equal to j less than ni, meaning that I have disks which move around. They never intersect until the first time they return, they are invariant by the time ni. And I have a nested sequence of such disks. And lambda is contained in the union, j goes from 0 to ni minus 1 of f of di.
Don't you need the ni's to be multiple, I mean, to have a...
They will necessarily be multiples just by the definition. Because since this is periodic of the period n1, this is periodic.
Yeah, you cannot choose them.
Yes.
That's
You need to choose them periodically.
Yeah.
And it's a consequence of this that f has periodic point of period ni. So just by having this infinitely renormalizable set, it's a consequence of Brouwer theorem of Brouwer-Omios that you have a recurrent point you have a compact invariant set for an Omio of the disk, you have a periodic fixed point. So this is for a power. This tells you that you have infinitely many periodic points.
Do you have to take an intersection and iterate over that? For each I.
For each I, this is so
so it doesn't have to be equal to the intersection.
It doesn't have to be equal to the intersection.
And you need the iterator of f.
And I need, yes, the j iterator f. Thank you. So it doesn't have to be equal to the intersection. I'm just saying that this is infinitely renormalizable over this, if this happens. And in particular, this is, if I have something like that, then f restricted to lambda is semi-conjugate to an odometer. Okay. What time did I start?
10 minutes late, so.
10 minutes late. Okay. So all of the things that we're going to do, that I'm trying to do here, are pretty much topological. So I almost never get conjugacies. I only get semi-conjugacies because you can always explode periodic points or explode orbits. So you don't usually get conjugacies to the objects, only semi-conjugacy. But the dynamics of here on the intersection is kind of the thing. It doesn't have entropy, which is something that I like, and it doesn't have periodic points also. I mean, you're just moving around and filling the space as you move around without creating much complication. So, okay, so let me try to explain a little bit of the results and the machinery, not the full machinery, but part of the machinery to obtain them, which is to describe zero entropy on the sphere and on the plane. So the first theorem is by Franz Handel, and then I assume that I have f from S2 to S2 Omio such that f has no horseshoe, and omega of f equal S2. So the non-wandering set of f is everything. This is the conservative case. This is in particular is something that always happens when you have preserved the Lebesgue measure, for instance. Then there exists a family AI of open invariant 6.3 topological annuli such that first the union of AI, if I take the closure of the union of AI, this contains S2 minus the set of fixed points of F. Second, if X does not belong to the union of AI, then the omega limit and alpha limit of this point X is going to be contained in the set of fixed points of F. And third, for each I, the function rho I from AI to 0, 1 is well defined and continues. So I need to explain a couple of stuff here. I mean, I just wrote the statement, but let me explain what I'm talking about here. I'm going to say that I'm going to do a drawing, and the drawing is going to help a lot. I'm going to find there are some fixed points here. And then in between these fixed points, I have something which is like some continuum that separates these fixed points. And every point in this continuum starts at a given fixed point and dies at another fixed point.
And so some of the fixed points are kind of elliptic light, and some are
this is kind of elliptic light. This is omega, so I don't have anything.
No, but light.
Yeah, this is an elliptic point. This is a saddle point. And I have also infinity is also a fixed point. I'm working on this field. And then here things also. So these are the fixed points. Then you can find the annuli, which is whatever is not the complement of these fixed points and the blue things. These are the annuli which are described there. The points which are not in the annuli either are born in a fixed point or die in a fixed point. And then in each annuli, I have this function, rho I, which I will define now, which is the function that gives the rotation speed in that annulus. So I think everybody is familiar with the theory of rotation number by Poincaré. So that when you have omega of the circle, you can define what is a rotation number, which measure the average speed with which you are turning around in the circle. In the annulus, when you have an omega of the annulus, and then since these annuli are invariant, you can also define a rotation number, which means you can sort of average what average speed which orbits are rotating inside this annuli. And there is a well-defined definition for that, but the problem is it's not clear and it's not true that you always have a rotation number. For Poincaré theory, for the circle, you always have a rotation number, and this is the same independent of the point. In the annulus, you might not have a rotation number, and it's usually not the same, because it usually depends on the point. So the theorem says that in each annulus, you're going to find that the rotation number actually exists. It's well defined for everybody. Okay, it belongs between 0 and 1, open 0, open 1, so it's a fractional rotation number. And this function is continuous, meaning that the level sets of this function are invariant invariant subsets of the dynamics, so I should draw this here. You're going to find here some invariant set, which is rotating with speed, say, square root of 2/2. Or you can find here some invariant set which is rotating with speed 1/2. You take this part, you move it this way, you take this part, you move it this way back. Okay? And if you apply this again and again and again, you get a finer and finer and finer decomposition. You see here the structure when you apply it to F2, the same theorem to F2 appearing. So that in some sense, the dynamics of conservative orders with zero entropy is pretty much integrable. I mean, it looks a lot like the dynamics that you would find for the phase space of the pendulum. It's not integral because it's possible that you have, for instance, an open annulus, and the dynamics is transitive, rotating with irrational speed. And you cannot have anything integrable because you have like this thick region which needs to be constant, where any integral needs to be constant. But other than that, you always find the same picture that you would expect from seeing in conservative flows. The theorem was first proved by John Franks and Michael Handel in their case they proved it for C-infinity diffuse and area preserving instead of non-wandering. The non-wandering thing is a little improvement. The other thing is their theorem was pretty much topological, but they needed Young-Dim result to calculate entropy, and that only holds in C-infinity. So most of the theorem was topological, but they needed a C-infinity machinery. So these new things we did, we kind of could be able to get rid of that and go directly to omnus. So that's the picture for conservative case. Okay. Now, what about non-conservative dynamics? So, in order to describe what happens in the non-conservative case, I kind of need to introduce what's the proper object work. So here, it's not the omega limit, it's the proper object that's going to be helpful for us. It's something called Birkhoff recurrence fluxes. So let me some definition first. I'll say that there exists a Birkhoff connection from X to Y if U neighborhood of X, V neighborhood of Y, there exists some n greater than 0 such that Fn of U into V is not there. So, and I'll denote this X, meaning that if I look in phase space, if I have a point X here and a point Y here, I'm saying that there is a Birkhoff connection from X to Y. If I take a small neighborhood here of X and a small neighborhood of Y, I can always find some point that goes from here to here. So that I can go up from arbitrarily close to X to arbitrarily close to Y. And then I'll say that say that X is Birkhoff smaller than Y if there exists x1, x2, xn such that x equals x goes to x1, which goes to x2, which goes to 3, which goes to y. So I say that x is smaller than, this is not a proper order because note that this is n needs to be greater than 0. So it doesn't follow that x has a connection to x itself. It doesn't have to happen. Okay? So this is not an order yet, but it will be in the set I'm going to define. And I define the set of x is Birkhoff recurrent if x is smaller than x. So I have to say that x is Birkhoff recurrent if I can have a cycle that starts at x and then ends at x. And now, in this set of the Birkhoff recurrent points, this is actually an order, and I can define an equivalence class. Meaning that x is equivalent to y if I can go from x to y, and I can go from y to x also. Okay?
You just go back.
Huh? So, then a Birkhoff recurrence class x. And it's easy to show that this is actually an equivalence class. This set of Birkhoff recurrent points, it lies in between. I mean, if a point is non-wandering, then it has a connection from itself to itself. If you go from arbitrary close to itself, you return to arbitrary close to itself. So then a non-wandering point is always Birkhoff recurrent. And if you are Birkhoff recurrent, you are chain recurrent. Because these, they just described there is a chain which small jumps at this place. Okay, so Birkhoff recurrence lies in between non-wandering and chain recurrence. So omega f contains Birkhoff recurrence f, which is contained in chain recurrence f. The classes are the other way around. If I have, if one set is smaller than the other, then the classes are the other way around. So the chain recurrent class is smaller than a Birkhoff recurrent class. And so it's I'm going to get lost if I stop here.
So how it is related to the Birkhoff center?
Huh?
The Birkhoff center, because between omega of f and time recurrent of f, you have the Birkhoff center, so that's, you take the non-wandering set, and then the non-wandering set of the f restricted to the non-wandering set, and then you continue in this way, and at the end you have a finite, you have a like transfinite induction, you can stop somewhere, and that's the Birkhoff center.
It doesn't. This goes the other way around because you're larger than the non-wandering set. In the other case, you're going downward. You have smaller and smaller substance. So this is larger than the omega limit. Okay, but one thing which is interesting is that if for any x, the omega limit of x is contained in a class. So if I describe classes, I'm also describing omega limits of every point. I'm describing omega limits. Okay? And then the theorem here says,
And not alpha?
Huh?
Just omega.
The alpha also, alpha limit of x. The alpha limit is also contained in a Birkhoff class. This class doesn't need to be closed, which is a little annoying, but it always have closed subsets inside it. For instance, if x is in a class, then the omega limit of x is in a class, and then the omega limit of x is closed, and you can use the omega limit of X as the closed set here. So theorem says that I have f from S2 to S2, omeo, no topological horseshoe, and B, a Birkhoff class. Then either so the question was here, what else could be find except from the things that we saw before? The answer is nothing. In some sense, there's nothing more else from what we've seen before. There's no zero entropy dynamics. There is not quantified what we saw as examples before. Then the Birkhoff class can be either one, every Z, which belongs to B, for this class, non-wandering. If I have a Z which belongs to B, okay, so sorry, there exists K greater than 0, such that every Z which belongs to B, which is non-wandering, has that omega Fk of Z is contained in the per K of F, and alpha Fk of Z is contained in per K of F, meaning that either you have a class where every non-wandering point is born in an orbit of period K and dies in an orbit of period K, or the second thing is B is an rush rotating set. Or the third possibility is that if lambda contained with B is closed and invariant, then let me try. Can people read here or should I go up?
That's nearly, yeah.
Then lambda is at infinity, topologically, infinitely renormalizable. Meaning that all three possibilities that we have is that either you have these cycles that we saw before, or you're going to have these irrationally rotating sets, which we had before, or you're going to have the dynamic is infinitely normalizable, and you have periodic points of arbitrary large period. There is a specialization of that for recurrent, for transitive sets. If lambda is a transitive set, this is also, again, I'm assuming that I have an omeo and no topological horseshoe, then either 1, lambda is a periodic orbit, second, lambda is irrational rotating set, or sorry, lambda is topologically infinitely renormalizable. And a final one, which is of particular interest, is don't like to present too many, but this is sort of like, this is just the same thing. I mean, just doing a little bit more specialization, is that if you have theorem, now I have F is a C1 diffil of R2, which is dissipative. This is an important case because people always study transition to chaos for dissipative systems, and in particular for Henon family and things like that. So if I have a C1 diffil which is dissipative, and then this is of R2, not of S2, but I'm just saying that it contracts area everywhere, so the derivative contracts area everywhere, and I need C1, then, and lambda is a stable transitive set. Then lambda is either a periodic point, periodic orbit, or infinitely normalized. Meaning that there are only two possible behaviors for a stable, for an attractor in some sense of the dynamic. Is that this third possibility, the second possibility, which is the rational set, cannot happen.
So what is stable?
Stable just means that there is a neighborhood of this set which is sent into itself, forward stable. Meaning that if you have a stable transitive set which is not a periodic orbit, if you don't have a trivial stable set, then you must have infinitely many periodic points of arbitrary large period and stuff like that. Okay, I should mention that there is a very fine result by Charles, by Corbusier, Pujals, and Perecer, solving a whole conjecture by Charles itself, I guess. And that says that if F is C2 diffil, and the entropy F belongs to the boundary of entropy 0, and dF is less than 1/4, then F periodic points period k to the 2 element n for n greater than 0 and some k and possibly finitely many. Meaning that, if I understood correctly, that the results show that this shows that if you have a infinitely renormalizable dynamic, then you're going to have periodic points or very large period. But in fact, if you assume a little bit more differentiability and a little bit more contraction, then you can get that you actually have a period doubling cascade. Meaning that this is the actual period doubling cascade that you should expect. And here, first, in this generality, this is not true. You probably cannot assume that you have a period doubling cascade because I can go as high as the derivative. So it can contract very little, and I can always construct examples where I have the odometer involved is not it is not like a doubling odometer, but you actually get a periodic disk of period 3 and then a periodic disk of period 4, I guess.
Yeah, you can get that if dissipation is not bounded away from one.
Yeah.
So, but the 1/4 is I think intuitive idea is that it forces you to get into a class of disaffective math which has been studied before by Sylvain
and Enrique and yeah, that shows that the have a settled and the stable manifold goes to infinity.
Yeah.
So you cannot stay in the bound. Yes.
That's why there is not it's a serious number.
Huh?
Not by the best number, but very good
It's the number when the hypothesis of the dissipation are satisfied, right?
Yeah.
But it's possible that this works for a better number than 1/4.
But essentially you cannot expect to have that.
Okay, so yeah, no, sorry, no topological Horseshoe. Okay, yes. No topological Horseshoe. I mean, I could say just no entropy, but this is a little bit bigger than try to.
Yeah. Each time you say no topological order, would you say no homoclinic orbit?
No, I mean it works, ohmios, so it doesn't need to be. I don't have differentiability anywhere.
Yeah.
So then topological Horseshoe is the best way to explain. But it could be just no.
But you have this type of if you do have, you don't have this type of behavior that you observe when it's not a homoclinical.
Yes.
It's not a horseshoe, but it looks like a horseshoe.
Yeah, I mean, if I have a horseshoe, I have something which looks like a stable set, but this could be a large fiber, and it's difficult to describe it. I have 5 minutes. Okay. Yes, they are all moving, right? No. First, this is semi-conjugate, not conjugate, so I can blow up a fiber. Okay. So that I could have a large fiber and not be. Second, this irrationally rotating set, it could be the hedgehog, which means that I can have here a periodic point, but only one, not more. So except from this case, I cannot have anything other than minimal line shape. And so that's it. I mean, here you don't have periodic points. Here I can only have one periodic orbit. Here there are two possibilities. I can have one periodic orbit, or I can have two and be the whole sphere, which is the irrational rotation. And I'm not going to try to show more of the techniques in 4 minutes because it wouldn't be very helpful. Maybe I'll stop here.
Are there more questions or comments?
It's gone.
It's gone.
Other people asking questions? So what was the definition of the irrationally rotating set exactly?
So that means that except for at most 2 periodic orbits, the irrational rotating set, so the irrationally rotating set is that your lambda is the union of disjoint lambda 1, sorry, all the way around, lambda 1, union lambda k. So it's the union of finitely many subsets. These are disjoint union such that f lambda I equals lambda I plus 1. So you permute these guys, and there exists some P and Q which are fixed. by fk, so that, I mean, by renormalizing, by taking a power of k, that I can assume that I only have one set, I have here some p, some q, and then my set is that means that for all z which belongs to lambda 1, z different from p of q. I'm not saying that p and q are in this set, but they might be in this set. That's the only thing. Then the rotation number of f S2 minus PQ. Sorry, there exists alpha which is not belongs to R minus Q. Z is alpha. And I need to define this. I'm just saying that if I'm in the sphere and I take out 2 points, then I get an annulus. And I can try to describe the rotation number of the point on the annulus. I'm saying that first that there is an irrational number such that first all the points there have rotation number, and this rotation number is the same and is alpha. So everybody rotates exactly with the same speed and an irrational
Other questions? If not, thanks. You can get it.